Question from 1997, past paper. Two small objects of mass capital M and 2m are released from rest at heights 2h and h respectively above the ground level. All right. So that is the ground level, and each object is released from different heights. They both have different masses as well. So this height is 2h, this height is h. And if you look at the masses, this is capital M and this is 2m. All right, fine. Respectively above the ground level. Which of the following is same for both masses just before hitting the ground? Right now, you have to, this part is very important. Neglect air resistance. So when air resistance is not there, we don't have to worry about a lot of things. Right, let's say this object is reaching the ground. When it hits the ground, it will have a particular velocity. I can take it as v1 for the time being. And at the same time, when this object hits the ground, it will also have another velocity. We'll take it as v2 for the time being. And initially, both the objects will have zero velocity because they are dropped from rest, released. Then you can use the energy concepts. You can say initial kinetic energy for both the objects, a common equation. Initial kinetic energy is equal to final potential, initial potential energy is equal to final kinetic energy. Initial gravitational potential energy is equal to final kinetic energy. Now, if you use a common equation, initial potential energy mgh equals final kinetic energy half mv squared. So we know m and m we can cancel out. V is going to be equal, v squared is going to be equal to 2gh. V is equal to square root of 2gh. My point is velocity or speed. The first answer, speed does not depend on the mass of the object if you ignore air resistance. We have ignored air resistance, so we don't have to worry about that. Velocity depends on height. We'll take this object as okay, capital M and capital 2m, right? Fine, never mind. So speed when reaching the ground, speed before hitting the ground. When you compare the speed before hitting the ground, they will not be definitely equal because they are released from different heights. But if you, in case if they ask us to compare before hitting the ground, between capital M and 2m masses, the speed will be highest for 2m mass, capital M mass, because it was released at a higher, from a higher level, or the height is high. Therefore, it should have been like this, right? Fine. And next one, kinetic energy. Now, talking about kinetic energy, initial gravitational potential is equal to final kinetic energy. Now, if you consider this equation for capital M, final kinetic energy is equal to initial gravitational potential energy. Final kinetic energy is equal to initial gravitational potential energy. We can write like this only because air resistance is ignored. And what is the initial gravitational potential energy for that object? That is capital M into 2h, g into 2h. That is actually 2mgh. Similarly, for 2m, if you consider, you can apply the same equation, final kinetic energy, it's equal to initial gravitational potential energy. And there also you can see it is 2m into simple g into h. Therefore, the answer is once again 2mgh. Therefore, since both the object has same initial potential energy, they will have the same kinetic energy when they hit the ground because air resistance is ignored or neglected. Therefore, second one should be the correct answer. Second one should be the correct answer. Right. Now, what about time of travel? Time of travel, if you take the time of travel, if you consider a common equation for the time of travel for an object falling under gravity, initially, let's say time is equal to 0 here. When it reaches the ground, time is equal to t. And let's say this is the height we are talking about. And it's 0 here. And the acceleration, we know if you ignore the air resistance, acceleration is going to be equal to gravitational acceleration. Therefore, you can apply the equation s equal ut plus half at square to get an idea. So s is the displacement, h initial velocity is 0 plus half into g into t square. Therefore, you can see t will be equal to 2h over g. This is t squared, and to find t, you have to take square root. This is the answer we are getting for time. Time also depends on height. Both the objects are not released from the same height, so time will be different. The mass is not considered because air resistance is neglected. So if air resistance is neglected, mass will not decide the amount of time needed. Gravitational force acting on masses, that is very easy now. For on capital M mass, what is the gravitational force acting? It is mg, capital Mg. And for capital 2M mass, we all know it is going to be 2mg. 2mg, right? Now talking about momentum. Momentum. Now, if you take capital M mass, when it hits the ground, its velocity is going to be this one. I mean, square root of the velocity is v equal to gh. We have already derived an equation, so it's going to be square root of 2g into 2h. So it's like square root of 4gh. Right? So the momentum for that object when it hits the ground is going to be m into square root of 4gh. That is the momentum of that object when it hits the ground. For 2m mass, when it hits the ground, let's see what's going to happen, right? When it hits the ground, the velocity of that is going to be square root of 2gh, because velocity does not depend on mass when it hits the ground. That is the equation. So there you can see momentum, it will be given by the equation 2m into root of 2gh. And you obviously can see these two are not the same, because this is from here, from the root, you can take 4 out, you will be getting 2m root of gh, whereas here it is 2m root of 2gh. So root 2 times larger for this object, the momentum, when it hits the ground. Therefore, the obvious answer is kinetic energy, second one. Next question is from the year 19. Right. What does it say? A particle falls freely from a height capital H above the ground. Which of the following graph represents the variation of its total energy with height? Total energy with height. A particle falls freely from a height capital H above the ground. Capital H above the ground. So the particle will be like this. This is the ground, and the particle is dropped here from here. All right. So at this point now, simple H will be equal to capital H at this point. And at this point, simple H is equal to 0. And when the particle reaches the ground, here initially it will have 0 velocity. And when it reaches the ground, it will have maximum velocity V. But the problem is, this question is about total energy. Since they have not clearly mentioned about air resistance or any resistive forces, we have to assume that there is no air resistance involved. If there is no air resistance involved, the total energy will be constant. The fourth will be the answer, right? But if air resistance is involved, then the total energy should reduce as you go down. But I don't think we have to worry that much here in this question, because they have not mentioned anything about it. Particle falls freely, and we can assume that the total energy will not change. The total energy will not change. But yeah, but be mindful, if there is air resistance, then there can be a change in total energy. Capital E is for total energy, but let's go a little further away from this question and let's focus on some other things. What will happen to kinetic energy and potential energy? That's something we can discuss. Talking about kinetic energy and potential energy, you have to assume that this is your zero potential level. What is the meaning of zero potential level? At that level, we can say the gravitational potential energy is 0. If you take that as our zero potential level, the ground is the lowest point of the motion, so we can take gravitational potential energy at that point as 0. And here, the gravitational potential energy at this point will be the maximum. Hope you can agree with me on that, maximum. And kinetic energy, talking about kinetic energy, at the maximum height, the kinetic energy will be 0. And as the object goes down, when it reaches the ground, since gravitational potential energy is 0, all the gravitational potential energy here is converted to kinetic energy. Therefore, when the object reaches the ground, kinetic energy will be maximum because there's only kinetic energy available there. And in addition to that, we all know total energy that should be equal to, throughout this motion, it should be equal to kinetic energy plus potential energy when air resistance is ignored. When air resistance is ignored. This is how the ignored, right? Sorry, when air resistance is ignored. This is how the relationship will work. Now, the graph is for height and energy. Height and energy. So we know gravitational potential energy, that is equal to mgh. Gravitational potential energy is equal to mgh, and we can say that gravitational potential energy is directly proportional to h. Hope you can understand this, because m and g are constants. Mass and gravitational acceleration is constant. Therefore, gravitational potential energy is proportional to h. And if you plot the graph for gravitational potential energy, your graph will be like this. Now, I will draw it in general, like energy. I'll take the y-axis as energy and x-axis as height h. When height h is 0, mgh is 0. As height increases, gravitational potential energy, where I have used red color, it will increase uniformly like this until capital H. Capital H is the initial point. And we all know that total energy, if air resistance is ignored, it is constant. So it's a flat line like this for total energy. Now the most important part is next. Now this line represents total energy, and the red color line represents gravitational potential energy. Now the question is, what will happen to time? Sorry, kinetic energy. Not time, kinetic energy. Kinetic energy will be opposite of potential energy. Like this. The graph should be a straight line, because when you add potential energy and kinetic energy, they are equal to total energy. So the if potential energy, this is a constant. Now total energy, people, it's a constant. We all know total energy is a constant. If total energy is a constant, what's the meaning of that? When kinetic energy increases, potential energy should decrease. When potential energy increases, kinetic energy should decrease. If potential energy increases linearly, kinetic energy will decrease linearly. That's what happens. Okay, so this will be the exact center point. When the height is h by 2, both potential energy and kinetic energy will be exactly equal. Right? So these are the graphs you can expect if you are supposed to plot the graphs for gravitational potential energy and the kinetic energy. Be mindful about that. This is for kinetic. The green color one is for kinetic energy. Right. Now, they might ask you another type of graph. That is this. Imagine you drop an object when time is equal to 0, all right? And the object, okay, it reaches the ground. Now, we all know when the object reaches the ground, it will have a velocity of v. And at this level, the height is capital H. At this level, the height is 0. But this time, it's going to be all about time and energy. All right? And now the next graph we are going to analyze is energy variation with time. Energy with time. And time starts from here. And we are supposed to plot the graphs. Let's say again, air resistance is ignored. That means one thing is for sure, that is the total energy. That is going to be a flat line like this. We will have a flat line for total energy like this. Right. So I've taken the time taken to reach the ground as, I'll take it as t naught. Yeah. So we will be extending the graph until time t naught. So until t naught, the total energy will be constant. No problem. Total energy will not change as long as air resistance is ignored. So this is total energy. Now we are going to plot the variation of kinetic energy and potential energy. How are the shapes going to be? Now, talking about kinetic energy is something which depends on velocity, isn't it? Kinetic energy is something depends on velocity. When you drop an object like this, velocity, if you draw the graph of velocity with time, if you draw the, first of all, you have to go for velocity. So velocity with time, you can say it increases like this, straight line, because it's falling under gravity, and we have ignored air resistance. Therefore, every second velocity will increase by 10 meters per second. This is the graph of velocity. And if this is the graph of velocity with time, the graph for velocity squared with time will be a curve which is bending towards y-axis. Hope you can understand this. Now, when time is 1, velocity is 10. When time is 2, velocity is 20. When time is 3, velocity is 30. But when time is 1, velocity squared is 100. When time is 2, velocity squared is 400. When time is 3, velocity squared is 900, bigger values. So what I'm trying to say is, kinetic energy depends on velocity squared. Kinetic energy is half mv squared. Kinetic energy half mv squared. Half m are constants. Therefore, kinetic energy depends on the shape of v squared. If the shape of v squared is a curve, kinetic energy is curve. If the shape of v squared is straight line, kinetic energy is straight line. With time, v square is a curve. Therefore, kinetic energy will also be a curve like this. For kinetic energy, we've been using green color, so it goes like this. This is the graph for kinetic energy. And we know when you add kinetic energy and potential energy, it should be equal to total energy. Therefore, the variation of potential energy has to be opposite of the variation of kinetic energy. So if it's similar to this graph, the kinetic energy graph, this graph, first graph. For potential energy, graph should be the opposite of this, like the mirror image of this. Therefore, you should plot the graph like this, somewhere like this. Sorry, the graph should be like this. The opposite of kinetic energy graph. That means in the answers they have given, you can go with the fifth one for potential energy. Sorry, not the fifth one. It's not given actually. It's not given here. Sorry, it's not given here. This should be the graph for gravitational potential energy. That means it should be opposite of kinetic energy. Because we know when kinetic energy increases, gravitational potential energy should decrease. Initially, the kinetic energy graph will have a lower slope. As you go towards right, the slope increases, right? The slope has increased. Same thing will happen to gravitational potential energy, but in the opposite direction. This is how the energy, the mechanical energy of the object will change with time. This is with height or distance. This is with time. Both are equally important. In future papers, they might ask about this. Next question is from 2000, year 2000. Two particles A and B have equal kinetic energies, but the velocities of the particle B is 4 times that of A. The ratio momentum of A divided by momentum of B. That's what we are supposed to find out. Right. So the easiest way of approaching, well, one of the easiest way of approaching this question is this: both have same kinetic energy. Kinetic energy of A is equal to kinetic energy of B. Therefore, you can say half MAVA square is equal to half MBVB square. So that's one equation you can quickly write down. Yeah, so this half will get cancelled off. Therefore, you'll be getting MA over MB is equal to VB squared over VA squared. That's one thing we can write down. And moreover, you can see this particle, but the velocity of particle B is 4 times that of A. So velocity of particle B is 4 times that of A, means this is the ratio between them. 4:1. VB is 4 times larger than A. Therefore, VB over VA is 4/1. If I substitute it here, it will be 4 squared over 1 squared. Therefore, it's 16/1. Okay. Now let's move on. Next, they are asking momentum of A over momentum of B. So momentum of A over momentum of B. What is the equation going to be? That is MA divided by MB, MA into VA divided by MB into VB. Right. So when you do a question, you don't have to write all these things. Just writing these things to explain you all. MAVA divided by MBVB. For MA over VA. Sorry, for MA over MB actually. For MA over MB, you can substitute the value of 16. Multiplied by, for VA over VB, you can substitute. Now, if VB over VA is 4, VA over VB is going to be 1 over 4. I can substitute 1 over 4. Therefore, the final answer is going to be 4. That's pretty straightforward, isn't it? So the answer for this question is 4, third answer.